Okay, let's start. Hi everyone. I'm Johann Friedrich, and I'm presenting my work published on 3DV about online video depth anything, temporally consistent depth prediction with low memory consumption. I'm from Heidelberg University, and if you have any questions, just post them in chat, and I do my best to answer them. Okay, let's. Okay, so depth estimation, as you might have known, is a very popular research topic, and methods for single image have shown that current methods are capable of predicting very precise and high quality depths like meters or prime depth. And with newer versions like depth anything v2, um, the race of who got the best depth prediction is basically on. And with Mode 2, we are actually able to predict metric scale depth for single images. But for downstream tasks, like video depth estimation is a little bit more interesting because most of the times we don't have a singular image, but a complete video. And the video actually gives us more information because we have different viewpoints. So like video depth estimation is of course a thing, and there's also a lot of research on this topic. So some examples are listed here. We have NVDS, Dust3R, and DepthCrafter, as well as online video, like video depth anything. And most of these methods, they rely on offline inference. So the idea is you have a video, like here on the top, and you captured the video, and afterwards you will take your whole video and then estimate the depth and utilize all information you have after capturing the video. But again, for downstream tasks like um, uh, robotics or autonomous driving, this is not what we want. We want actually an online method, which in best case also runs on very low power hardware. And since this work is sponsored by Harman International, that's what we're interested in. The idea here is that we capture a video, and as we capture new frames, we predict the depth of this captured frame basically immediately, and then we can react much more quickly to whatever changes we have or navigate through the video as we capture the video itself. And when checking, there are actually some methods which provide a tool for online depth estimation, but they are all tested on H100s, which is a very, very powerful GPU normally used on clusters and oftentimes not available, especially if we talk about robotics or autonomous driving. Um, so it would be very great to have a method which runs efficiently online, and we don't have to sacrifice any performance. And this is what our goal is. We searched through some methods to get the best starting point and identified video depth anything as a very good starting point. And this is why. So I just put the video from the web page of theirs on here. And the idea is that video depth anything offers very high quality, as you can see on the right, and good performance. And it is trained on a lot of data, so it has a huge video prior, but it is running on a relatively small network. The cons of this, I mean, it's offline, so it requires the whole video during inference, and it uses a lot of VRAM, which we need to fix somehow. And this is where our idea and method comes in. So let's dive a little bit more deeper in how video depth anything actually works, and then what we modified to achieve our online version of it, which we call online video depth anything. So let's start with video depth anything. The idea is you got your whole video, and then we um, divide it into smaller batches of 32 frames each with a small overlap. Then this batch of frames is encoded with a Dino V2 encoder, which is, as you might know, an image encoder. So that means that this actually encodes each image individually. And for each image, we get a representation, which we call here feature 1 to 4. And these are then processed by a relatively small spatial temporal head. So to give you some context, the small version has 6 million parameters. And everything which is marked green green here is where actually the reasoning about temporal, also about the time in the video, is done. So these are in the motion modules, the rest is again single frame. As an output, we will get a def batch of, again, 32 frames, and then we do this for all the batches of the video, and we align them, because this is a scale and shift invariant method. We align these batches, which might have slightly different scale and shifts, to each other using the overlap, and get then a consistent video in the end, which is of high quality. But however, these motion modules and the handling of the 32 frames in parallel, that requires a lot of VRAM and of course forces the model to be offline because we always have to wait for 32 frames at least. And then if we want to align it with the previous ones, we have to wait for the next batch as well. So there's a lot of basically buffering, which we want to avoid in an online setting. So let's summarize how this looks like. So for the, as I already told you, the only thing where we actually do reason about time and the like timing in the video, that is the motion modules. And the motion modules basically consist of two attentions, and the attention is not masked or anything. So every frame can attend to everything. That means that future frames can influence the past and the other way around. So the past can influence the future, which is of course not allowed in an online setting. And we calculate everything in parallel, which is computational wise very efficient, but in our online setting not possible. How our online setting in contrary looks like is like this. So we have some frames where we have predicted a depth already, and then we got a new frame in, and we want to predict the depth for this new frame. So this means that the past is fixed. What we have predicted once, we can't change it anymore, and and the past, of course, can influence the future still. So depending on the scale and shift we predicted here in the first frames, we need to adjust accordingly to this one. And also the first, like the frames of the past might give us a lot of information we want to use or reuse for the current frame. And then, of course, we only want to really do calculate the depth for the current frame. And since for the other ones, we have calculated it already. And if we think about this a little deeply, that is very similar to what large language models do. And that's one of the key insights of our work, that we can use methods of large language models to make make the video depth estimation faster. The idea is, like, if you compare the task, it's, as I said, pretty similar. So in a large language model, we have a sequence of words. For example, this is a picture of A, and then the task is to predict the next word. In our case, we have a sequence of images, and the task is to predict the next depth of the next input image. So how can we make use of this? Let's zoom a little bit into the motion modules. So this is what it looks like in video does anything. We have our batch, and then we do some reordering, which is technically necessary, but the important part is the attention here. So for each frame within the batch, we calculate queries, keys, and values using a linear layer. And of course, like strictly technically speaking, it's a little bit more complicated, but for the to make it a little bit easier, we just can think of it about calculating one key, query, and value for each frame. And then we calculate our attention over the whole batch. In our online version, that's a little bit different, and that's exactly what large language model will also do, and it's called KV caching. That means that we have our input image, so the current image we got, and then we calculate query keys and values only for this single image, and then we save it in a cache. So as the name suggests, KV caching, we save the K and the V into the cache itself. The cache may contain some queries, keys and values of frames we've seen earlier and already saved this, and then we can reuse all the saved information and the current information to compute our attention only for the current frame. And then this just repeats for every attention in the whole spatial temporal head of video depth anything. You also need to note that for this, we actually don't need to change any weights. So the we didn't introduce any new parameters, right? So we can basically just reuse the weights from the original video, if anything, and look how it works. For inference itself, we need to also start the inference somehow, but that's pretty easy. So what we do, if we start the video, we only have just one frame, so our cache is basically empty, and then we incrementally fill the cache. So for the first frame, for each motion module and each attention within the motion module, we just save the keys and values. And if we come to the next frame, we just append it in our cache, and so on and so forth. Um, so theoretically, we could do this for the whole video, but in practice, we run out of VRAM pretty fast. And since we want to do it online, we also run out of compute. So what we stick to it for the first test is we just take the batch size of video, if anything, which is 32. And if the video is longer than 32 frames, then we basically just reject the oldest frame and replace it with the newest one. So like a sliding window over the video. Okay, so as I said, we don't need to replace any weights by default because we didn't introduce new parameters. And then we get results like this. As you can see, the latency decreases by quite a bit, which is nice. That's what we wanted. And also the VRAM consumption also goes down, which is nice, but also the metrics go down. So the method is just much worse with this new inference strategy. And why this happens is also pretty quick explained. So basically, the weights are trained in such a way that they like assume that they can influence the whole batch. But doing our inference now, only the latest frame comes in and can be changed, and everything else is fixed. So the model just struggles with the slightly shift of it. This means we need to fine tune it in the end, but fine tuning is much easier because we can use all the prior knowledge from video, if anything, for our online method and basically just steer it in the right direction to understand the new nature of the task, basically. So how do you fine tune? Again, we get inspired by large language models. The idea is pretty simple. We use mask attentions. That's the gold standard for large language models. I'll quickly explain it. So during training, we want to stay efficient. So therefore, we also use a batch of frames. We put it through our model, but instead of calculating the full attention, we mask our attention. That's basically what mask attention means. And what this intuitively means, I'll quickly explain here. So we have a bunch of input frames in our batch, and the masking, it's a diagonal or causal mask, just like zeroes out the attentions in such a way that the first frame can only see itself and only attend to itself, while the second frame can only attend to itself and the first frame. The third frame can only attend to itself and the second and the first frame, and so on and so forth, so that you have a very nice causal mask in the end. We also noticed that this is not quite enough to get to a good level of performance, and therefore we needed to adjust the loss. And so we start off with, again, the video def anything loss, which is shown here. It consists of two parts, and they are pretty quickly explained. So we have a scale and shift invariant part, which is basically just a scale and shift invariant loss on the batch. That's why it's called scene and not the normal scale and shift invariant loss you might know from meters. And a temporal gradient matching loss. Again, this is for temporal consistency to get a nice consistent video in time. And the idea is that if between two frames in the ground truth, the change should be the same as the change in two consecutive frames of your predictions. So that's what the temporal gradient matching loss enforces. However, as I told you before, video def anything predicts batches and aligns them to the same scale and shift afterwards. And in our online setting, we cannot do this. So we need a third loss term, which enforces the model to predict always the same scale and shift, no matter how the scene might evolve during the video. And this is where our scale and shift consistency loss comes into play. I try to explain it in the visualization here. So what we do, we get our batch of predictions out with the mask attentions, and then we copy it. So we had to have it twice. The first copy, we take our ground truth for the first frame and calculate the scale and shift for only the first frame and apply it to the whole batch of predictions. And the second part, the second copy, we take every frame individually and calculate the optimal scale and shift for each frame individually, and then we calculate the difference for the scale and shift consistency loss. What this intuitively does is if the scale and shift for each individual frame is the same as the scale and shift for the first frame, the loss reduces to zero. So it enforces the model to predict consecutive frames with the same scale and shift as the first one, which is exactly what we want. And if we now fine tune it, we get the following results. So we keep the nice low latency and the low VRAM consumption, but our metrics are now much better and much closer to the original video depth anything. So our oVDA is now very close to the video depth anything. It's not quite there, and there's a good reason for this, because video depth anything can basically utilize information from future frames, which our online version by design cannot. So therefore, it's expected that it's a little bit lower, and also that we enforce the method to always predict the same scale and shift from the first frame is, of course, always also a little bit more difficult, because you can imagine if you have a wide scene with everything basically very far away, and then suddenly someone, some person or a sign, whatever comes in very close to the camera, the range needs to adjust for this, and that's a little bit harder for the network to predict. Okay, this is very nice, but now we want to make it so fast and so efficient and consume as less VRAM as possible to make it run on an edge device. And the most easiest thing you can think of is just reducing the caching size or the context window. And this is what we did here. So since attention's complexity in calculations grow quadratically, we just halved the context size. So we instead of saving 32 frames, we save only 16 frames. And we can see that this like thirds the VRAM usage, and also improves the FPS, but the metrics itself, so the performance stays virtually the same. And therefore we decided to use the oVDA with a cache size of 16 instead of 32 as our main method. And we tested it on an NVIDIA Jetson Orion NX. And on there it runs with 20 FPS, which is quite impressive, while maintaining the performance I showed you here. And therefore we are able to outperform all our competitors with while running on a Jetson, while all the competitors are tested run on an H100, which is very impressive in my opinion. So we can check the video. It's looking quite sharp and nice. And we can see that it's also temporally very consistent. Let's, as the last thing, let's check out the competitors. I'll quickly introduce and walk you over the different methods we are showing here. As I said, these are all online methods, so where the video comes in frame by frame. We have here cut3r, which is a method which builds an internal 3D representation of the space and then updates it as new frames come in. This is very efficient and also leads to quite good results, but since that's very expensive to keep this 3D representation, it only works on rather low resolution images, which is why it's a little bit blurry. Then we have NVDS, which takes a single frame method, in their case I think it's meters, and trains a second network to make it temporally consistent and smooth it out, which again has the smoothing effect. Then we have ChronoDev, which is an online method, but it's based on a video diffusion model. This means that it's basically virtually impossible to run it on an edge device, and it's very slow, even on an H100. And then we have the FlashDev. That's a method basically using LSTM, so long short-term memory blocks on top of def anything v2. And this struggles a little bit with temporal consistency. So let's check out. So our method is in the middle here. And now we can see the comparison. I hope it's at least a little bit visible, or via the Zoom stream. If not, then please check out our website. So here you can see that NVODS and Cut3R, they are both much more blurrier than our solution, and FlashDev is a little bit sharper, but it struggles with temporal consistency, which we can see if we now basically have the side-by-side view here. So you can see that when the video starts running, that here this depth plane is very consistent throughout the video for our method, while it flickers and jumps around for the two flash depth versions. Okay, so to summarize, we introduced KV caching to reduce the graphic cards, memory, footprint, and enable online inference of video def anything to make it to our method online video def anything. We also introduced a new loss, a scale and shift consistency loss to reduce flickering and to get the scale and shift consistent over the whole video. And we also publicly released the code to run our method on an NVIDIA Jetson and achieve 20 FPS, outperforming our competitors while still running on an edge device, which is, I think, very cool. Thank you very much for your attention, and I'm happy to answer questions.
Awesome. Thank you very much, Johan. Yeah, there's a few questions in here. Um, One of the questions here is about the motion module. So,
Yeah.
does each motion module have an attention mechanism? And
Yeah,
also, how
so
do you
oh,
select
sorry.
how many motion modules are used?
So basically, this is that's what well video does anything. So the model we are founding ourselves our online version on is just introduced, and each motion module consists out of two attentions, which are just stacked after each other, and they have four motion modules in their head. So in total, we have eight attention blocks within the um, complete head, and these are the only ones which argue about temporal consistency and temporal relations. Yeah, I hope.
And is the KV cache quantized? If yes, did you check how the quantization impacts the VDA results?
Yeah, so in the paper, we actually did some tests, especially for the edge device. That's important, right? So in the normal implementation, it's, I think, not really quantized. So we just use float 32. And then for the edge device, I think we got like scaled it a little bit down, but the details are in the paper, so you can just read it yourself. It doesn't influence the metrics and that much, but the runtime gets a little bit faster. So yeah, it depends on which implementation you're using in the end.
And there's a couple questions here about the latent cache. One is, how does the latent cache size trade off against accuracy, temporal consistency, and VRAM? Is there a sweet spot, and does it shift between an edge device or an H100, A100?
Yeah, I mean, again, it's depending on what you want in the end. So I showed you the ablation here. That the C minus 8 just means that we reduce the cache to 8, 16, and 32 respectively. And you can see that there is a trade-off. In our opinion, the C16, so the model with the cache size of 16, is the best, the sweet spot. But if you really want to squeeze out the most and you're really concerned about the VRAM on your edge device, which is a big thing actually, especially if you're running robotics, then you might want to use and reduce the cache size to 8, so to squeeze out a little bit more. Um, Especially, I think if you want to steer a robot, 43 FPS is not really needed, so you might get away with like 10, and then you would need the like additional VRAM you freed here, so then you might want to go with the C8 version. And if you want all the best quality, you should of course go to C32. But yeah, it's depending on what you're using. But I think the version with the context of 16 is the best compromise of everything. Yeah.
And a question here is probably a good question to ask while the slide is up. It's, how far back does this latent cache effectively reach? Is there a point where the older frames stop contributing? And is that ceiling set by quality or by VRAM?
Yeah. So in like as we can see here, I think the quality is not that much affected by the how far frames reach back, but this is heavily depending on how fast things move in the video. So these are Davis videos we show here, and all the metrics are computed on Kitty, which is rather stable, I would say. But if you now have a video where there's a lot of things happening very, very fast, then you would need a much wider cache, of course. We actually experimented with alternating the cache, so basically trading context length with VRAM, but that didn't work out quite well. You can find all the details in the appendix of our paper. But to summarize it, we basically said, okay, we can cache every second frame, but therefore use like to compensate for this, we use two caches, and then we alter between the caches to give you an idea. But the model struggles to keep the same scale and shift for both caches, which therefore results in like kind of a flickering stuff and reduce the matrix heavily. So yeah, I think there is a lot of research to be done, and I think there are also a lot of methods used for LLMs, which we didn't apply here, which one could apply, which basically tackle exactly this problem to extend the context length without increasing calculation complexity. Yeah.
Yeah, and I'll make this the final question here. I think it goes nicely after your last statement, but the question has to do with the LLM cache tricks. Were there any that you considered but skipped, like sliding window, attention sig, KB quantization, page
Mhm.
attention? And do they map onto video latents, or does the cross-frame redundancy call for something else?
Yeah, we unfortunately didn't go that far into this, so we didn't test all these tricks then. But I think that would be a nice step for future work to go into a little bit more into the details. There, I would assume that the redundancy plays a big role, so that you can throw away a lot of information if because there's a lot of redundancy in consecutive frames. And maybe one should get inspired by latest video encoding models, which basically handle the same problem. But the time we were working on this, it wasn't such a big thing, so it was only in the coming. So I guess there is quite a lot of potential to even squeeze out more performance without losing any computational time or VRAM. Yeah.